Alright, welcome back everybody. Today I'm going to be completing part D of homework 3 for separations. What we're going to be doing in this first part of part D is we're going to algebraically and geometrically go over the material balances for the envelopes, including the stripping and rectifying sections of a distillation column with a total condenser. And then we are going to use those material and energy balances, go over how they're similar and how they can produce similar triangles on the Panchon-Savarit graph that justifies the Panchon-Savarit graphical method. So getting started here, we're first going to draw out a sketch of our rectifying section, something that we've done quite a few times in previous videos. So of course, as I mentioned before, we've got our total condenser up here. And then below that, we'll have a stage. Coming up from that stage, we'll have a vapor flow coming out of our condenser. Make that line a little bit longer. Coming out of our condenser, we of course have our distillate flow and then our reflux stream. And then we've got a QC, you pull it out of the condenser. And then below this stage, we can consider another stage with vapor and liquid, and then one more stage with vapor and liquid flows. And then, as usual, we start with our condenser being considered the zero stage before any of the stages. So this stage here, we could consider it to be stage n-1. We can consider this stage to be stage n. We can consider this stage to be stage n+1. And then, as we were saying, we're going to draw an envelope around this column for what we're going to consider here. And looking at this envelope, we know that we've got vapor coming up here from our stage n+1. So we've got Vn+1 coming up right here. And then we've got liquid coming down from our stage n, our Ln. And then we've got our distillate flow coming out, our D. And that's all we have for our material balance. And like we've done in several previous videos, we're going to go ahead and write out our overall material balance, which is that our Vn+1 is going to equal our Ln plus our D. And then something different we're going to do for this video that we haven't done previously is we're going to go over the energy balance for the rectifying section, as both the material balance and the energy balance will be important in justifying our Panchon-Savarit graphical method. And the energy balance is very similar. We've got our Vn+1 times our molar enthalpy H bar V at n+1 plus our QC, that heat being removed from our condenser, is going to equal our Ln times our molar enthalpy of our liquid at stage n plus our distillate flow times our molar enthalpy of our distillate. And that's our overall energy balance. It's also going to be important to have our compositionally broken down material balance. So as we've done a bunch of previous times, we can say that Yn+1 times our Vn+1 is going to equal our Xn times our Ln plus our Xd times our distillate flow D. What we're going to do to proceed here is we're going to sub in this overall material balance into both our energy and our composition balance down here in order to solve these and get these into a form where they both look similar so we can compare them for this Panchon-Savarit graphical method. So we'll go ahead and get started first with the compositional material balance here. So you can say that Yn+1 times our Ln plus D, so we're subbing in for that Vn plus 1, it's going to equal our xn times our Ln plus xd times our d. Then, of course, we can rearrange this, and we're going to rearrange it to isolate both our Ln and our d. And what that's going to give us is our Ln times our yn plus 1 minus our xn is going to equal our distillate flow d times our xd minus our yn plus 1. And then we can rearrange this farther to get it into another form that allows us to compare these two values with respect to ln over d. So we're going to divide over that d to get that ln over d times our yn plus 1 minus our xn is going to equal our xd minus our yn plus 1. And that right there is the form that we're going to want that material balance in. We're going to come back to that in just a second. But first, we're going to have to sub in this expression into our energy balance as well. So what we're going to get from that is our, go ahead and do it over here. We're going to get that our molar enthalpy of our vapor. I'm going to drop the n plus 1 and the n on our molar enthalpy is just because if we know we have the vapor molar enthalpy or we have the liquid enthalpy, we know that the vapor is always going to be associated with that n plus 1 stage and the liquid is always going to be associated with the n stage. So there's really no need for the extra handwriting and extra space to be taken up here. So I'm just going to call these h bar v and h bar l going forward. So anyway, we've got our h bar v, and then we're subbing in this overall material balance for our Vn plus 1. So we get our h bar v times our Ln plus d is going to equal, add my plus QC here as well, plus QC is going to equal our Ln times our h bar L plus our d times our h bar d. And like we did previously, I'm going to go ahead and isolate our Ln and our d. So once we rearrange this equation a little bit, we can get that Ln times our h bar v minus our h bar L is going to equal our d, our distillate flow, times our h bar d minus our h bar v. And then, and then I have to, of course, add our QC. Keep forgetting that. And then, like we did before, we're going to rearrange this expression to divide out our d here. So once we divide out that d, what we get is Ln over d times h bar v minus h bar L equals h bar d minus h bar v plus QC over d. As you can kind of start to see here, we've got this Ln over d, and in both cases, on either side, we're taking our something to do with our vapor stage at n plus 1, we're subtracting out our liquid stage, and then on the other side, we're taking our distillate minus our vapor flow, which all kind of lines up between these two expressions. We can kind of start to see where we're going to be able to relate our material and energy balances here in some sort of graphical method. But before we get to that graphical method, I'm going to go ahead and define one more variable. So right here, you can see that we have our h bar d plus our qc over d. And what that essentially is our change in enthalpy for our distillate, because we've got our molar enthalpy for our distillate, and our qc divided by our d is essentially normalizing that qc to the molar flow rate of the distillate. So overall, we can call this value here our delta D. And this delta D is going to be our starting point for our rectifying justification of our Panchon-Savary. So let's get to the actual graphical method we're talking about here. So the Panchon-Savary looks something like this. On the y-axis, you've got enthalpy, molar enthalpy, and on the x-axis, you've got composition. Then you got these two lines that look something like this. With this top line representing the saturation vapor and this saturated liquid. And what we're going to start with here, we're going to say we know that our delta D lies somewhere up here at an enthalpy somewhere up here at our concentration or our composition of our distillate, our XD. And from here, as we go down the column, we're going to be moving something like this from our saturated vapor to our saturated liquid. And as you can see here, we can kind of start to create some triangles here. And the first value we're going to notice is this right here, going from our distillate enthalpy down to our vapor enthalpy. And as you can see from our equation right here, this value, I'm going to move our delta D explanation here. We can see this line here is associated with this expression here, so we're going to call this A. The reason they're associated is because we're going from that distillate enthalpy down to our vapor enthalpy here on this saturated vapor line, and that's exactly what we're doing when we're taking this expression here. We're subtracting our vapor enthalpy from our distillate enthalpy. So we're going to call this expression here A, and this A represents this line here, which we're also going to call A. And then we can also look at this change in enthalpy here, this line, which we're going to call B, and that's associated with the difference between the vapor enthalpy and the liquid enthalpy, which, as you can see on the other side, we have with this expression right here, this HV minus HL. So we can call this B. So we've got our A and our B for our changes in enthalpy on our y-axis, but we're also going to have is these changes in composition. So going from this XD over to our ym plus 1, we got our value C right here with our, here it is, our overall material balance for the Panchon-Savary. So we can call this line right here C as we're going from that XD over to our ym plus 1. You can see that difference right there. And then the final line we're going to define here is this line D, which of course is going to be our last variable here, and that's the difference between our vapor composition at n plus 1 and our liquid composition at stage n. We can call that D. And what you'll notice here is that if you divide over these expressions, we see that A over B equals ln over D, and C over D equals ln over D, which means logically that A over B must equal C over D, which shows us a direct comparison. It shows us we have similar triangles between our energy balances and our material balances, which allows us to justify this Panchon-Savart graphical method for the rectifying section. So next up, what we're going to do is we're going to do pretty much the same exact thing, but for our stripping section, the whole derivation is going to look very similar, and we're going to get to the same idea that we can relate these material and energy balances and use those to justify this Panchon-Savart method, except we're going to start somewhere over on this region towards our stripping section. So I'm going to go ahead and get all this erased, and then we can go ahead and move on to our stripping section for our Panchon-Savart justification. So give me 1 second to erase all of this writing here. Just before we move on to our stripping section, I want to explain something real quick. So as you can see, this monitor here is usually turned off, and just to show that I'm not cheating or anything here, if you look at like what I've got on here, this is just the canvas for the course that I was reading through the problem statement. So no cheating or anything. The tabs are just the lecture videos, all that stuff. Just wanted to clarify that before we got into any kind of trouble here. All right, now that we've completed our rectifying section for our Panchon-Savart, we can go ahead and do our stripping section. And the reasoning is going to be very similar for the stripping section. We're just going to look again at our basic little schematic for our stripping section. We've got our reboiler here. Just putting in a QB heat to reboil. We have our vapor coming up from N+1, our liquid coming down from stage N, and our bottom flow coming out. And this time we're just going to draw the envelope right around this reboiler here. So it doesn't really change a whole lot to add in those extra stages. So from this, as we've said a bunch of times before, we can say that our Ln must equal our Vn+1 plus E. And then we can do our energy balance. And like before, I'm going to leave out the N+1 and the N on our molar enthalpies just because it's kind of tedious to write all those subscripts in. So we're just going to say that our H bar L times R Ln equals H bar V times our Vn+1 plus H bar B times our bottom split B. And then I also need to add in, keep forgetting the Q's. QB, and that is going to equal our H bar B times R Bn+1 plus our H bar B times our bottom split B. And then we can also do our compositional material balance here. So we can say that our Xn times our Ln is going to equal to Yn+1 times Vn+1 plus Xb times our bottom slope B. And then similar to what we did before, I'm going to go ahead and sub in our overall material balance into this compositional one, which is going to give us Xn times Vn+1 plus B equals Yn+1 times Vn+1 plus Xb times our bottom slope B. And then similar to what we did before, I'm just going to rearrange all of this to get our Vn+1 and our B isolated. What that's going to give us is that Vn+1 times Xn minus Yn+1 must equal our bottom slope B times our Xb minus our Xn. And then, as we did before, I'm just going to divide out that B, which is going to give us Vn+1 over B times our Xn minus Yn+1. It's going to equal our Xb minus X10. And that is going to be our stripping material balance we're going to use for our punch-on saturate. So now we can go ahead and move on to the energy balance. We're just going to do the same thing here. Say that our H bar L times Vm plus 1 plus V plus R QB going to equal our H bar V times Vm plus 1 plus R H bar V times V. And then as we did up above, we're going to rearrange this, solve for our Vm plus 1 and our B, which is going to give us Vn plus 1 times H bar L minus H bar V is going to equal B times H bar E minus H bar L minus our QB. Not yet. Getting a little ahead of myself there. Minus our QB. And we're going to multiply both sides by -1, just get it into a form that makes a little bit more sense, which is going to give us our Vn plus 1 times H bar V plus H bar L going to equal. And then we'll do 2 steps in one because I don't want to take up our entire whiteboard with derivation here. We're going to multiply both sides by -1 and divide over our B everywhere. So that'll give us Vn plus 1 over B times H bar V plus H bar L is going to equal R H bar L minus our H bar B minus our QB over B. That all checks out. So now we have both of our expressions here, and if you remember from our rectifying section, we defined a delta D. Here we're going to go ahead and define this right here as our delta B, our change in enthalpy at our bottoms, and the way that works out is the same as the delta D did. We've got our molar enthalpy of our bottoms flow coming out, and then our normalized Q to our bottoms flow to get our molar enthalpy being added in by Q. That defines our delta B. And yet again, we're going to go ahead and draw out our graph here. So at the bottom, we've still got our composition, our H bar, and we've got our 2 lines here, with the top one representing the saturated vapor, and the bottom one representing the saturated liquid. And this time, since we're starting at our bottoms here in our stripping section, we're going to define our delta B as being right here at our XB, our bottoms composition. We're going to draw our line to the vapor. Here I'm starting out there. Wrong kind of line here. I'm going to move up to our vapor here. And then, similar to what we did before, we can see our change in enthalpy here. We can call this A. And that A expression is going to be this right here, going from our bottoms to our liquid enthalpy. And then similar to before, we can define this line here as our B, which is going to be going from our liquid to our vapor enthalpy, which is this value right here. And then we can go from our composition at our XB all the way over to our XL. We're going to call that line C. Where did I put this? There we go. That right there is going to be C. And then we got our line going from our liquid to our vapor. We're going to call that D. As you can see here, that right there is our D value for our stripping section. And similar to before, we know that C over D is going to equal our Vn plus 1 over B, and then our A over B is also going to equal Vn plus 1 over B. So we must know that C over D is going to equal A over B, meaning that our Panchon-Savart is justified and we have similar triangles between these two sections. Now for the stripping section as well as the rectifying section. And that, I believe, is the end of the first part of homework D, where we are justifying the Panchon-Savart graphical method. So now we can move on to do a little bit of a more real example in Python. So I will see you in that part of the video.
All right, welcome back to Homework 3, Part D for separations. Now, we're going to be doing the Python segment of our Panchon-Savart segment of our Homework 3. And to get started with that, I went ahead and put our second problem statement in here. So we're going to use these conditions, a 45-65 mole percent methanol isopropanol feed with 96% distillate recovery of the methanol, 98% mole percent purity, and a reflux ratio of 5. We're going to generate that Panchon-Savart diagram we've been talking about up on the board here computationally, and then we're using that. We're going to vary our reflux ratio and see how that affects our Panchon-Savart diagram. But to get started here, as the problem statement up here discusses, our components are going to be methanol and isopropanol. So I need to go ahead and run our CHE tools so we get that to work. But then we're going to say that our P is going to equal props, and we'll say methanol and isopropanol. Propanol. Perfect. Sure that runs all right. And then our next step, we're actually going to need a lot of old code that we've made from previous homeworks. So we're going to pull from some of our previous homeworks. I'm going to copy over our bubble T NRTL calculations from that previous homework, as well as some of the accompanying code that goes along with that. So because we're going to need those bubble T's so that we can calculate our enthalpies we were talking about up here for the vapor and the liquid. So I'm going to go ahead and copy those over. All right, so as you can see, I went ahead and copied these over. So what we have here is, like I was talking about, our bubble T and RTL calculations from previously, where we're using these CHE tools to calculate our bubble T at our given pressure, which we're going to specify as 10,000 pascals. And then this is all just calculating each of these bubble T's for all of our X's and our Y's so that we'll be able to later calculate our enthalpies, which is going to be our next step. We're going to use a P-chip interpolator to find the certain temperatures at which we're also going to find these enthalpies. So getting started with that, we're going to say that first that our X int, our X interpolator is going to equal our scipy.optimize.pchip interpolator, and we're going to go off of our Z1s and Y1s. And then next we're going to need our TX interpolator. So we're going to say TX int is going to equal scipy dot optimize dot pchip interpolator. This time we're going to do the Z1s and the bubble T's from up above. And then we can say that TY interpolator is going to equal scipy dot optimize dot pchip interpolator Y1s and then our bubble T's. Fantastic. So we can use these TY and TX to then calculate our enthalpy, create our interpolators for our enthalpy for our liquid and then our enthalpy for our vapor. So moving down, we can say that our HLs are going to equal P dot HL, which is one of our tools from our CHE template. Remember the HL. You can say our X1, 1 minus our X1. And then we can do our TX int at our X1, and we are going to do that for X1 and Z1s. Perfect. And then we can say that our HVs are going to equal P dot HV going from our Y1, oops, put a bracket there, our Y1, 1 minus our Y1, and then need to get out of that bracket. We can say that our TY int for our Y1. And then we're going to do that for Y1 and Z1s. And that will give us a couple, our HLs and our HVs from our TX interpolator, and then we're going to be able to create an HL interpolator and an HV interpolator from these values that we just found. So now we can see our HL int is going to equal, again, our scipy dot optimize dot pchip interpolator for our Z1s, HLs. Then we can do the same for our HV interpolator, scipy dot optimize pchip interpolator, again for our Z1s and our HVs. We can shift enter that. Hold on. Sorry about that. I put optimize instead of R interpolate, so this should fix that. Fingers crossed. All right, we are all good with our interpolators now. So now we can go ahead and start putting in these base case things were provided up here. So to get started with that, we are going to assume that our feed is just going to equal 1 mole per second. We're going to say that we know our ZF class, we talked about it being 0.45. That's our feed composition of our more volatile component. And then we talked about how our recovery in the distillate from up above here is going to be 0.96. And then we also know that our reflux ratio is initially going to equal 5. We know that our XD, our purity in our distillate, our volatile component composition in our distillate is going to be that 0.98 that's described in the problem statement. And then we can also calculate our weight of our distillate, our WD, and that's going to be our ZF times our F times our recovery in the distillate, which will give us our weight of our distillate. And with that, we can also find that our distillate flow is going to be our weight of our distillate over our composition of our distillate. And then once we know both our distillate and our feed, we can find our bottoms, which are going to be equal to our feed minus our distillate. And then we can kind of work backwards from knowing our bottoms in order to find our weight of our bottoms and the rest of the associated, the XB, all of that. So initially, we are going to calculate our weight, our bottoms, which is going to equal our ZF times our F minus our WD, our weight in our distillate, and we can find our XB, and that is going to be equal to our WB calculated above over our B. And going past that, what else are we going to need? That should be all of our variables we're going to need. So now we can go ahead and calculate our QC and our QB, that being the heat we're pulling out of the condenser and the heat we're putting into the reboiler, which we talked about up on the board just a second ago. And to calculate our QC, we can kind of reorganize one of our equations we figured out up on the board here and take our HV int, our HV at our XD, and we can subtract out our HV, our HL, interpolate at our XD. And then to get our QC, what we're going to do is we're going to multiply this all by our R times D plus R. I believe that's correct, because that's our L over D times D would be our L plus our R, which should be all good. Or we're adding our D to that because that's our D plus our L, which is all of the liquid components coming out of the condenser. So that should be our QC. And then from there we can our delta D, which we know is going to be equal to our QC divided by our D minus our HL interpolate at our XD. That again is from those equations we derived previously up on the board. And now that we have that, we're going to go ahead and find our QB, which is going to be equal to D times our HL int at our XD plus our B times our HL int at our XB minus our F times our HL int at our ZF input composition, all plus our QC. And then we can go ahead and find our delta B, which is our delta B is going to be equal to our HL interpolate at our XB, all minus our QB divided by B. And that should be all of our algebraic terms that we're going to need for now. So we can go ahead and move into defining some root functions so that we can get each of our y values on our Panchon Savret that we're looking to graph here. So go ahead and shift enter there. So first off, we can go ahead and define our f root for our rectifying section as a function of y and x. And in this function, we're going to define our HL as our HL interpolate of our X values. It's all good. Then our HV is going to be the opposite, going to be our HV interpolate of our Y values. And then we're going to go ahead and return delta D minus HV all times Y minus X all minus HV minus HL times X minus our XV. And that will be our function that we can do a SciPy root on later on once it comes to actually graphing our Panchon saturate. So that's for our rectifying section, but we also need one for our stripping section. So we're going to define fruit strip as also a function of y and x. And we are going to say the exact same thing for our HL and our HV in here. We're going to return something a little different here. So we can go ahead and copy this down and change a couple things in here. So we're going to return HL minus delta B over HV minus HL times, this time X minus XB. I believe that is all good for our root functions. So I think that we are all good to start making our loop to go ahead and create this plot. You click Shift Enter, make sure that's all good. So moving on to our plots, we're going to go ahead and start with the unanimous fig equals make underscore subplots. And then the first thing we're going to have to add to this is going to be our two lines representing our saturated liquid and our saturated vapor on our Panchon saturate that our tie lines go in between. So to do that, we're going to do fig.add scatter, and we are going to say that our x equals our z1s, our y is going to equal our HL interpolate of our z1s, and then we're just going to go ahead and change up our line color a little bit. So once we get to our final graph, it's going to look nice and pretty. So we're going to say our line color is going to equal cyan. Very good. And then we're going to do the same thing for our other tie land, our bottom. We're going to do fig.add scatter. We're going to have our x is going to equal our z1s yet again, but this time our y is going to equal our hv interpolate of our z1s. And this time our line color, we're going to make that equal to red. Fantastic. So those are our two lines that all of our lines go in between there, that saturated vapor and saturated liquid line that we move in between on the Panchon saturate. So now we're good to move on. So now we're going to go from our top point at our XD all the way down that first initial line going from XD down to our saturated liquid line. So to do that, we're going to say fig.add scatter, and our x is going to equal xd. Our y is going to equal our delta d, as we just discussed. That's the enthalpy point up there, and then also our HL int of our XD. And once we get to doing the rest of these lines, I'm going to make generally our lines coming down to our Panchon Sabre blue. So I'm just going to set our line color equal to blue for this initial one. We'll get the rest of them as we go through our for loop that we're about to build. So moving on from there, we are going to go ahead and initialize our y. And we know that we're starting, as we set up here, at our xd. So we're going to go ahead and start that value out at xd. And then we're also going to add the switch in, because we need to know when to switch from doing the lines down from our delta D to moving up from our delta B. So we're going to start out with our switch equal to false. Now that we have that switch function outside of our loop, we can go ahead and say for I in range, do 1000. We are going to find our x's based off of our y. So we're going to say that our x is going to equal x interpolate based off of our y values. Or x int, not x interpolate. Not making a function here. And then going on from there, we need to graph each of our tie lines based on if this switch is working or not. So we're going to say that, or not if the switch is working. If we're done, once we've hit our bottoms composition, we want to break out of this. So we're going to say if x is less than xb, we're going to go ahead, if x less than xb, we need to go ahead and break out of our loop so we're not stuck looping forever. We need to break out of it eventually so we can actually get our plot. But once we have this break, hold on, I need to put a colon here. So we have this break function, we can go ahead and add our tie line. So you can say fig.add scatter, say x equals brackets from y to x, and then our y is going to equal our HL interpolate for our x's, and then our HV interpolate for our y's. And then we are going to go ahead and do our line color equal to gray. Since these are our tie lines, we don't want them to be too popping out, or else we're going to have a crazy rainbow. I'm not going to really be able to interpret it very well. So we're just going to set those lines equal to being gray. And then we can go ahead and put in another loop where we're going to say if not switch, because like I said, the switch is when we're switching over from coming down from our delta D and then going to switch over to coming up from our delta B down at the bottom. So if our switch is false, or if our switch is not false, then we're going to be coming down from the delta. So we're going to say fig.add scatter. Then we're going to have our x is going to equal xd, and then our x interpolate based off of our y. Perfect. And then our y is going to be going from our delta D, as we said up above, all the way down to our HL interpolate based off of HL underscore interpolate based off of our x values. Because this is coming from up at our delta D, so we're making those tie lines down at first, and then once we get to the switch, we're going to be able to go from our delta B going up to the vapor curve at the top. So it should be all good. And then we can go ahead and say else. We're going to do fig.add scatter, going from x equals our x is going to equal our xb, and then our y values. And then our y, similar to up above, is going to equal our delta b, and then our hv interpolate based off of our y's. And then for both of these, I'm going to go ahead and say our mode is going to equal lines, and that our line color is going to equal blue, as these are those big lines coming down from our XB and our XD. So mode equals lines, line color equals blue. Fantastic. And then up here, I'm also going to do the same. Our mode equals lines. Fantastic. All right, now we're going to need to have a function to make that switch happen. And to do that, we're going to go back up to our root functions here, and we're actually going to take the root of them. So we're going to call the root of our rectifying section our yrec, and we're going to set that equal to scipy.optimize.root scalar. We're going to do f root. First, we need to do a lambda y fruit rec for our y and x, with our x not equal to x, and then we're going to do the same with our y strip. So we can say a y strip is going to equal scipy.optimize.root scalar. Again, lambda y, our f root strip yx, again with our x not equal to 0. And then we're going to go ahead and compare these two values and say that if y strip is greater than yrec, we're going to set our set our switch equal to true. And I think I forgot up here, we need to do dot root, or else we're going to run into some problems later where it's not going to spit out a value. It's going to be spitting out like a big table that they're going to have to look at. So we need to do that dot root so we get a float value. So once we are switching that switch, we're going to want our y to equal the minimum between our yrec and our y strip. Just realized I put should be if our y strip is less than our yrec, then our switch is going to equal true. And then we've got that y minimum between our y strip and our y rectifying to switch our y values. And then our last step here is just do a little house cleaning when it comes to just making this figure look nice and pretty, getting the layout looking right. And the first thing we're going to do is do a fig.update layout. We're going to do update y-axis actually first. And we're going to go range equals, we go from delta b to delta d, just so that we're seeing only what we need to see on this graph. And then finally, we're going to do fig.update layout, and we will make it a nice 600 by 600. And we'll show that show legend equals false because we're just going to have a bunch of trace 1, 2, 3 all the way up to however many we have, which should be really annoying. So we're just going to get rid of that. Then fingers crossed, shift enter. Oh boy. Something's wrong here. Give me just 1 second. All right, I found out what was wrong. So what I did here is I realized, so first you can see all of our gray tie lines here are not facing the right direction. The issue there was that I had reversed my X and Y for my Y equals when I was first putting those lines in there. So I went ahead and fixed that. And then I also went ahead and I went up to I saw that my delta D was way, way, way too high. So I went up here and investigated that for a second. Where'd it go? And I realized that for my delta D, I was subtracting my liquid enthalpy, which of course was going to screw everything up there. So I'm going to go ahead and run through everything again. And there we go. That looks like a beautiful Panchon-Savart graphical representation right there. We have everything fixed. So the last part of this problem is to see what changing the reflux ratio is going to do to our graph down here. So I think first thing we can do is we can just go ahead and drop it down to, say, 1.5. Might have went a little too low. Yeah, clearly you can see what happened here. We're never even transitioning down to the bottoms because we just have so much reflux that like everything is just coming straight up to the top here. It's a really tight separation there, and as you can see, our delta B went way higher up, or our delta D went way higher up, so we're having to pull out a whole lot more energy there. And then let's go ahead and increase it up to, let's say, 15. And here you can see now our delta D is way up in the positive, and there are far fewer steps you take. Our axis has become super separated here. And I think that is the end of homework 3, part D. So I'll see you in the last one.